Welcome to the tour of the solar system. We're going to go through all of the major objects and just do each one really briefly. So we're going to start with the sun. The sun is 99.9% of the mass in our solar system. It's the nearest star to Earth. It generates its energy through nuclear fusion. It turns hydrogen into helium. As we go through, you might need to pause the video if you want to write anything down, but I'm just trying to introduce everything. It's also in the textbook. So Mercury is the closest planet to the sun. It's also the smallest planet. It has no atmosphere and it has a cratered surface. Venus is the second planet from the sun. It has an incredibly thick atmosphere compared to Earth. It's the hottest planet. The Russians have sent probes to Venus, and not long after they land, their electronics melt. So it is incredibly hostile to life. We should never go there. After Venus is the Earth. Some fun facts about the Earth is it's the only planet that we know of with tectonic plates. It's the only planet that we know of with an ozone layer. It's the only place we've ever found life. Mars is losing its atmosphere. Mars has the biggest volcano in the solar system. It has frozen water on it. There's lots of interesting stuff about Mars that we'll get into later. Most of the asteroids that we've discovered stay in a stable orbit between Mars and Jupiter, and we call that the asteroid belt. There are plenty of asteroids that stray out of it. We try to track those, but for the most part, they're in the asteroid belt. The frost line probably isn't going to make any sense until we get another chapter into the book, but I wanted to have it here in our layout, so at least you would remember where it is in the solar system. And that's going to really matter when we form the different planets. Jupiter. Jupiter is the biggest planet in the solar system. It's mostly made out of hydrogen and helium, much like the sun is. It's got over 60 moons. It's got faint rings. It's got some huge storms on it. There's the Great Red Spot, a couple other hurricanes. Some fun facts about Saturn is that it's the planet with the best rings. All of the Jovians have rings, but Saturn's are the best. Saturn, as a whole, is less dense than water. So if you were to have an imaginary bathtub, it would float. Uranus. In this photo, you can see the faint rings that Uranus has. Uranus also has storms when it is switching seasons. Uranus is the planet with the most extreme axis tilt, so it's going to have the most extreme seasons. Neptune is the last major planet in the solar system. It used to have a gigantic storm on it, but that has since faded. It's gone now. Neptune is a beautiful blue because of the methane gas in its atmosphere. The Kuiper belt is a comet belt, and the asteroid belt was left over from forming the terrestrial planets. The Kuiper belt is left over from forming the Jovian planets, so it's leftover comets. The Oort cloud is a huge, vast region around the solar system. This figure doesn't do it justice. See, look, distance is not to scale. Right? The Oort cloud is this vague region around the solar system where if Jupiter tossed a comet out of the solar system, we'd say it's out in the Oort cloud. If Saturn tossed out an asteroid, it would be out in the Oort cloud. So the Oort cloud is kind of the debris field of stuff that's gotten tossed out of the solar system. So we are going to be talking about how we think the solar system formed. And when we talk about that, it's going to be called the nebular theory, how the solar system formed. But before we actually describe to you what the nebular theory is, the textbook would like to point out some things about the solar system that the nebular theory is going to have to explain. So we're going to go through them in order. We're going to look at the ordered motions of the planets. We're going to look at the types of planets. Briefly mention asteroids and comets again, and point out some weird stuff in the solar system that we can't really explain, but we need to at least allow for them to happen. So, ordered motions in the solar system. All of the orbits roughly look like concentric circles. I know they're ellipses, but roughly they're pretty circular. And all of them are aligned pretty close to the elliptic plane. So I tend to think of the planetary orbits as grooves on a record. Earth is in this groove, Mars is in the next groove out, Jupiter is further out. Grooves in a record. And that cartoon works fairly well for me most of the time. Like a record, which always spins in the same direction, all of the major planets orbit in the same direction. Since we're in the northern hemisphere, let's say counterclockwise. If you're looking down at the Earth from above the North Pole, it orbits and rotates counterclockwise. So a running theme for our solar system is counterclockwise. It's not a perfect rule, but it's pretty good. So let's go through some of the stuff that goes counterclockwise. The sun rotates counterclockwise. All of the planets, most of the asteroids, and most of the comets orbit counterclockwise. Most of the planets rotate on their axis counterclockwise. There's two exceptions. Venus actually rotates clockwise. And Uranus is neither here nor there because it's tipped on its side. There's two main types of planets. We're going to call them terrestrial, which pretty much means small and rocky, and Jovian, which means what most people would call a gas giant. Terrestrials have a solid surface that you could walk on. They have thinner atmospheres than the Jovians. Like Venus is amazingly thick compared to Earth, but Venus is nothing compared to Jupiter's atmosphere. And they're relatively small. So here's the terrestrial planets. They're also all closer to the sun than the Jovians. For the Jovians, that's these four out here. They don't have a solid surface at all. If you were to land a probe on Jupiter, you would never touch ground. You would just go into denser atmosphere, until at some point you're like, hey, I think I'm in a liquid. Deeper into the ocean, liquid, deeper, until eventually the pressure would crush your probe. Which we've done. We've thrown a probe into Jupiter. Jupiter and Saturn are mostly hydrogen and helium gas. Uranus and Neptune are mostly what we call hydrogen compounds, so water, methane, and ammonia. So we could say there's all four of these. They're mostly, hydrogen and hydrogen molecules. The four biggest planets are also the lowest density. They're not made up mostly of metal and rock. They're mostly made up of gases. And so as a whole, they're more massive, but they're less dense. And the four outer planets, the Jovians, are also the bigger ones. The asteroid belt is left over from the terrestrial planets formation. So I like to think of them as pieces of rock that haven't really been touched since the beginning of the solar system. Right? They haven't gone through any volcanoes, they haven't gone through any tectonics, they haven't been under an atmosphere. The Kuiper belt, which you probably want to think of at first as the comet belt, is the leftover from the Jovians. They are pretty much the same thing, but icy. A lot more ice. And the Oort cloud. I already told you that that's the big field of ejected objects that's around our solar system. And we have to allow for the weird things that we see. So our hand wavy answer is going to be it probably got hit by something big while it was forming. Some of the weird things that we see is Uranus is tipped on its side. How did that happen? Well, maybe it got hit with something big while it was forming. Venus is rotating backwards compared to everything else, but it got hit just right at just the right angle, and that stopped the planet's rotation and turned it to clockwise. Now, there would have been a huge amount of debris. Proto-Venus there would have had huge impact marks on it. It would have been catastrophic, but everything would have settled back down, and today all the evidence is erased by volcanoes. When we get to the nebular theory, I'll tell you that we think the planets formed by absorbing asteroid impact after asteroid impact after comet impact. So they formed through bombardment. And that would have been especially active right at the beginning of the solar system. So right at the beginning of the solar system, we call it, and it's an awesome name, the era of heavy bombardment. None of the other terrestrial planets have a large moon, and large meaning comparable to its own size. Venus has no moons. Mercury has no moons. Mars has 2 teeny tiny moons, but they are pretty obviously captured asteroids. So we can't explain why Earth has this large moon. We've had several ideas about how the moon formed, but the one that we still have that hasn't been ruled out yet is called the giant impact hypothesis. And basically, a protoplanet ended up crossing our orbit and slamming into Earth. This would have been before there was life. This would have been before there were even oceans, possibly even before there was an atmosphere. So, no big deal to us. So after it impacts the Earth, huge, catastrophic destruction. This is what I imagine happening to Venus when its rotation is being changed. Right? Huge amounts of debris. Some of that debris might have been ejected out into the Oort cloud. Some of that debris, actually most of it, probably rained back down onto Earth. But some of the debris would have been able to set up a stable orbit. Over time, gravity will clump it all up into a moon. So the moon rocks that the Apollo astronauts brought back and tested are amazingly similar chemically to Earth's crust. Surprisingly close. The moon rocks and Earth rocks look really, really similar. So that supports this idea that maybe the moon formed out of debris from the Earth. Another thing that it might help explain is why the moon actually has a very small core for its size. It doesn't have enough metal in its center. Third thing it helps explain is maybe why Earth's axis is tilted. There are a couple other things in the solar system that I can mention that are unusual. A lot of the other moons in the solar system, at least the smaller moons, don't follow the rules of the solar system. They don't orbit near the ecliptic plane. They're not going counterclockwise. So maybe the reason for that is they didn't form with Jupiter. Maybe Jupiter captured them. And if you capture an asteroid or capture a comet into an orbit, it can end up in a very strange orbit. So in this figure, the red line is Jupiter's orbit, and Jupiter would be right there in the middle. And around it, these blue circles, these blue ellipses, are some of the orbits of its moons. And they're not very organized. Some of them are clockwise, some of them are counterclockwise, some would be up over the pole. Right? Jupiter's large moons follow the rules. Saturn's large moons follow the rules. But one of Neptune's big moons, called Triton, actually doesn't follow the rules. It orbits clockwise, and it is quite tilted from the ecliptic plane, so it's not on the flat record that most of the solar system is. Maybe it was a gigantic comet and it got captured by Neptune's gravity.